Today, we're diving into the top 15 breakthroughs in quantum computing from 2025, all backed by credible updates from labs, universities, and companies around the world. Stick around until the end, because the number one breakthrough is something scientists have been chasing for decades. But first, what exactly is quantum computing? A normal computer thinks in zeros and ones, flipping switches on or off. A quantum computer, though, can be both at once, exploring countless possibilities simultaneously. That's why it holds the key to solving puzzles classical machines choke on, from drug discovery to climate modeling to cybersecurity. Now let's begin the countdown. 15. Climate and energy modeling with quantum algorithms. Managing a power grid is like juggling thousands of flight schedules at once. The number of possibilities quickly explodes. In 2025, IonQ and Oak Ridge National Lab tested a hybrid quantum classical solver, scheduling 26 generators across a 24-hour window using a 36-qubit system. At the same time, researchers applied quantum solvers to tsunami dynamics and fluid flow equations. These aren't just flashy demos. They're the start of better renewable energy planning and more accurate climate forecasts, areas where classical supercomputers often struggle. 14. Drug discovery acceleration. Drug design is often bottlenecked by molecular simulations, understanding how proteins fold or how RNA structures behave. In 2025, IBM and Moderna used IBM's Heron chip to model RNA strands up to 60 nucleotides, while IonQ and Capu Quantum simulated protein folding with 12 amino acids. The systems are still small, but they chip away at the slowest steps in drug R&D. Each advance moves us closer to a future where vaccines and treatments can be developed at record speed. 13. DARPA's US2QC program. Quantum computers today are powerful, but noisy. Errors creep in constantly. The ultimate milestone is fault tolerance, systems that can detect and correct their own mistakes. In 2025, DARPA advanced Microsoft and PsiQuantum into the final phase of its US2QC program. The goal now isn't theory. It's building and validating a truly useful, error-corrected quantum machine. Coming from the agency that helped seed the internet and GPS, this signals that fault-tolerant quantum computing is now a national priority. 12. Quantum interconnect breakthroughs. Instead of one colossal chip, the future may lie in linking smaller quantum modules, just like data centers in the classical world. In 2025, Oxford scientists connected two ion trap systems with light, teleporting a quantum gate at 86% fidelity, and even running Grover's algorithm with 71% success across both chips. Meanwhile, superconducting teams demonstrated chip-to-chip links at 99% efficiency in under 100 nanoseconds. These milestones bring the dream of modular quantum data centers much closer to reality. 11. Optical tweezer arrays for neutral atoms. Imagine thousands of atoms suspended in place by beams of laser light, like marbles floating in invisible bowls. In 2025, researchers at Caltech scaled this vision to over 6,000 atoms, achieving 12-second coherence times and greater than 99.99% accuracy when reading them out. On smaller arrays, teams also hit 99.5% fidelity for 2-qubit gates across dozens of atoms. Neutral atom systems now combine both massive scale and high precision, positioning them as one of the strongest candidates for building the first million-qubit quantum computers. 10. Pascal expands to Saudi Arabia and South Korea. French startup Pascal, a pioneer in neutral atom processors, made headlines in 2025 not for a lab demo, but for expanding manufacturing to Saudi Arabia and South Korea. At first glance, that may sound like corporate news. But it's more than that. Scaling quantum isn't just about better physics. It's about robust supply chains and global reach. By establishing production hubs in multiple regions, Pascal is laying the groundwork for quantum as a worldwide industry. It's one of the clearest signals yet that this technology is leaving the lab and entering the real economy. 9. D-Wave simulates magnetic material dynamics. Modeling the behavior of magnetic materials, tracking billions of spins interacting simultaneously, is brutally hard for classical supercomputers. In 2025, D-Wave's quantum annealer stepped up, simulating these complex dynamics more efficiently than top classical methods. It's a rare but important milestone, a practical quantum advantage, not just a theoretical one. While annealers differ from universal quantum machines, their strength in solving physics. 8. Certified randomness on Quantinuum's H21 randomness might sound simple, but it's the bedrock of encryption, secure communications, and global finance. In 2025, researchers from J.P. Morgan, Quantinuum, and U.S. labs proved quantum can deliver it at scale. Using Quantinuum's 56-qubit H21 trapped ion system, they ran a certified randomness protocol, producing numbers that are mathematically guaranteed to be unpredictable. That's a first. Instead of trusting chance, we can now prove randomness itself. 7. Quera's magic state distillation breakthrough. For 2 decades, quantum scientists have repeated the same warning. Without magic state distillation, fault-tolerant quantum computing is impossible. Why? Because the process takes messy, noisy quantum states and purifies them into reliable, high-quality ones, essential for error correction. In 2025, Quera finally pulled it off at scale. This achievement is enormous. 6. D-Wave simulates false vacuum decay. Here's one that sounds like it belongs in a science fiction novel. In 2025, D-Wave used its advantage system to simulate false vacuum decay, a phenomenon in quantum field theory that describes how the universe itself might jump between energy states. Classical supercomputers can't even attempt this level of math. But a quantum annealer can. This wasn't just an engineering demo, it was an exploration of the very laws of physics. 5. Google's Willow processor, 105 qubits. In 2025, Google unveiled its Willow chip, a superconducting processor with 105 qubits. But the real story wasn't just the qubit count, it was what Willow achieved. For the first time, researchers demonstrated below-threshold error correction. Instead of errors multiplying as more qubits were added, error rates actually dropped. That's a turning point. It shows that scaling up can make quantum systems more reliable, not less. 4. Fujitsu and Riken's 256-qubit quantum computer. In April 2025, Fujitsu and Riken launched a 256-qubit superconducting quantum computer, quadrupling their earlier 64-qubit platform. It instantly became the most powerful quantum machine in Japan, and put the country on track to hit 1,000 qubits by 2026. Beyond the raw numbers, it marks Japan's formal arrival as a major player in the global quantum race. For years, the US and Europe led the field. Now Asia is stepping forward in a big way. 3. Rigetti's Ankaa-3 with 99.5% fidelity. In 2025, Rigetti made waves with its Ankaa-3 processor, an 84-qubit superconducting chip that reached 99.5% 2-qubit gate fidelity, the highest ever achieved on its platform. Fidelity is the lifeblood of quantum computing. It measures how often a quantum operation performs exactly as intended. 2. The UN declares 2025 the International Year of Quantum. Not every breakthrough is measured in qubits. In 2025, the United Nations declared this year the International Year of Quantum Science and Technology, marking 100 years since the birth of quantum mechanics. Why does this matter? Because it shines a global spotlight on the field. Governments, universities, and industries are now being encouraged to invest and collaborate on an unprecedented scale. 1. Microsoft's Majorana. 1. Topological qubit chip. At number 1 is Microsoft's Majorana 1, unveiled in February 2025. The first chip built around topological qubits. These qubits are expected to be far more stable, naturally shielded from many common sources of error. Constructed from a new topoconductor material, a blend of indium arsenide and aluminum, the chip currently runs only a few qubits. But the architecture is designed to scale. In theory, millions of hardware-protected qubits could be packed onto a single chip, slashing the massive overhead normally required for error correction, and making large-scale quantum computing practical at last. Experts still debate whether Microsoft has conclusively demonstrated genuine Majorana states, but if validated, this breakthrough could redefine the future of the entire field.